In this part, the last time I didn't know what to do about it, that there was a error. We're going to vary that resistance R1. Note that this is given that a variable, define a variable within that parenthesis, second parenthesis R val. This is the define a variable, and then we give a command here. It's called this dot step. Step dot not set dot step, and I call the parameter. The parameter is the R val, and if you're saying that here you define that within the parenthesis R val is a variable, the value is a variable. You come here, you got to step it. You say parameter, and say parameter name is R val. The list them 20, 100, and 150. And with this one, we're going to run that a pulse response. The pulse, pulse. We put a pulse there. We're going to see a transient response for 2 milliseconds, and that's to set it up. Now, once you go there, go to set it up. Once you go to setup, we want to run a transient response from 2 milliseconds, and that's what you do. This is the, now if you look through that, this is this, the activated that transient response. The rest of them are not active. Now this time it should work. I'm sorry I missed that. It's not a, this is not a set. It's a step. This is the function. Is a step. Okay, now it should work out. Let's go there. If you run the simulation, then you run it, and then you got to run the simulation. Now we put those the value there. We want to feed the voltage across these three, and if you want to value across the three, that's what you got. Like you can see that. Like now the other one, I should let me also plot that the trace for this input. You can see the input, and this you can see the input is a step wave 1 volt. The output is that output is depending on depending on what is the resistance you got. Now what is the value resistance? Obviously that with the peak one, with the peak you have the high peak. Obviously you have that for 2, and then the second one is like a film. The 100 is like a 500. 500 is that is very damped. It's very damped. Even it doesn't go to 1, and this one is go over like a 220 is like a over it's like a under dam. It does go, there is an overshoot there. That's why it's very important, especially for circuit, to know what value you have. It's the damping factor is very important. Now you can see that this is a very useful tool if you want to see that the values of different values, which is the optimum value there. You can define like that. You can see that in this particular case, if your input is a 1, if you got the circuit set up with the 20, you could have like you could have like more than 1 to 130% more than that. Like you can adjust anything you like that. Like this is very important. You can define the inductor, capacitor. Even you can define that variable as a voltage source. So you can see if you vary your sources and how that your circuit will behave. You got a source there. If you so vary the source, how is going to happen? I thought that with this one, it now clarifies that there are all the options you got. If I'll mention to you that if I mention to you the simulation, there are a lot of options you can do that. This is when we look to the transient response and AC response and DC sweep and noise analysis. We didn't do that. DC transfer is made like a Thevenin's, Thevenin's equivalent. You put a voltage source, you see where it is, and you where it is, and where your output, it will be given equivalent input resistance, output resistance, and the gain of the circuit there. The DC operating point, and it's like this, the DC analysis. If you'd be like a basic circuit, mostly you do the DC operating circuit, and that's what it is. Okay, I think that concludes that the introduction to your simulation, especially simulation for LTspice. If you want any other devices, let me go quickly for that. You can look for this voltage sources, then current sources, the transistor, and other one. If you look for miscellaneous, the one, you can have op-amps and miscellaneous circuit. You can have a battery. There are other built-in circuit. You can have the SCR, a silicon control rectifier. Silicon control rectifier. You got other types of transistors, jumpers, you name it. That you got a lot of them. You have that. If you're looking for a battery, like a pure battery, is that one. There are a lot of like a variable resistance you have. There's a variable resistance. You got a triac, and you got signals, like a signals, you got AC, DC signal source, you can generate that. There are some, you can see that specifically sometimes you connect a lot of resistance for some applications in parallel, and there are a lot of values you can have, you want some 1K, like a mixture of them. Sometimes you can do that. These are the one you can get that one. There are some of them, some other devices are there, and you just explore whatever you need. If you want to look for a cell, the battery cell, like if you got a solar panel, you got a solar cell there, voltage source, you got a cell, you can define it as a cell, as a voltage source or current source, otherwise that. And there are some other power devices, diag, and these are the one you can have that one too. Okay, this is a thought I mentioned to you. There are other devices there. You got a comparators, digital device. You got a digital, you got the filter products, and you got op-amps, the options. There are a lot of options. You got like power products. You got a power products. You can have the power products. A lot of power products you can have that too. Okay, I think that's what it is. One of the things I did not mention to you, and if you go to the setup, there is a control panel there. If you go to the control panel, there is a control panel is very useful. What is useful like that? You got especially the SPICE simulation that you may have to adjust them. This is the absolute tolerance of calculation, because SPICE simulates. The SPICE look into your circuit. If you got a resistance, is the voltage and current. It's like voltage and current related to resistance, like V is equal to the V is equal to the I is equal to V by R. And now if you look at an inductor is equal to L di dt, the voltage is equal to the derivative of that, the current. If you got an inductor, and if you got a capacitor, the voltage across the capacitor is the integration of that current. But whatever they do on that SPICE, once you mention that, like if you look to the particular circuit, that you got a R1, that the node 1 and 2, node in 1 to voltage is node voltage 2, and node voltage 1 difference is Ri, and the R times the resistance, and the inductor is L, the voltage across is L di dt, the capacitor is L, integration of these, the current to the capacitor. And when you have that, the SPICE or any SPICE, it generates a matrix. It creates a matrix and solve them, the matrix, and then find out all the variables, like a voltage and current. Like here, this is you're looking for absolute tolerance of 10 to the power minus 12, and the real tolerance of that all voltage and current, real tolerance. And then you got like a voltage tolerance, like a real tolerance, the current tolerance there. And then these are the main one. You got the absolute tolerance of all voltage and current. This is the real tolerance of current, and this is the voltage tolerance. These are the three things you're more important. This is all of them. This is the GM is one of the resistance. Anywhere there is an open circuit there, whenever that your resistance of this is the resistance you will have. If you got a resistance, the maximum it can have that resistance 10 to the power at the 12 1 over GM, and the absolute value is minus 12 is the voltage and current accuracy, and this is the real tolerance of the current. And then when you do this, like this, what you call this tolerance of all what you call it does the integration. That's the tolerance you got, and that's the voltage tolerance. Most generally the current and the voltage is, if you are look at the microvolts range accuracy, if you are dealing with 100 volts or 1000 volts, 10,000 volts, if you're looking for those accuracy, the SPICE will never find an operating point. That will give an error. That's why, depending on that, and depending on if you're looking for 1000 volts, you a circuit in 1000 volts or 1000 M, you have to reduce that accuracy of them. You cannot have the microvolts. You may have to, like the volts level of 0.1, 0.01 volt. These are the ones sometimes you have to adjust them. Otherwise, the circuit will fail. Of convergence problem, it's going to find a difference. I think that's the end of this one. I hope that it's going to help you to run the SPICE, the LTspice simulation, and that's the end of it. Okay, and